Now what do we have? So given a pi, I know how to find V pi. Okay, given a pi, I know how to find V pi. But finding V pi is not our goal, right? Not our ultimate goal. I mean, it's good to know how to find V pi. Our ultimate goal is to find pi star or V star, right? So I want to find the optimal policy or optimal value function or the optimal value function, right? So how do we do that? So that's the next thing we are looking at. So let's say that we have given V pi for some policy pi, right? For the purposes of this discussion alone, let's assume that we will be looking only at deterministic policies, right? And again, for finite MDPs, there always exists one deterministic optimal policy, right? So that's something to remember. For finite MDPs, always one, at least one. Finite MDPs have at least one deterministic optimal policy. Okay. So remember what we mean by finite MDPs. The set of states is finite, the set of actions is finite. Okay. And for MDPs with large number of states, I mean infinite number of states or continuous states or continuous actions, you can still say that about the existence of these optimal policies under certain technical conditions. So we are not going to get that. So most of the theory that we will develop is for finite MDPs. Right? So they will have at least one deterministic optimal policy. We will stick with that for the time being, right? So suppose we have some deterministic policy pi, some arbitrary deterministic policy pi, and we have computed V pi, right? We computed V pi, right? So let's pick some state S, right? So pick some arbitrary state S. When would it be better for me to perform an action different than that given by pi? Remember, for deterministic policies, I can just say pi of s, right? Pi of s is equal to the action that has a probability of 1, right? All the other actions have a probability 0. So I don't have to write pi of a given s, I can just write pi of s and the output will be an action, it is not a probability. So we are kind of abusing the pi notation. So sometimes the pi outputs an action, sometimes pi gives you a probability, right? So pi of s in a deterministic setting is giving you an action, right? I want to take an action A that is different from what pi of s tells me. And I want to take an action A that is different from what pi of s tells me. So when do I do that, right? So think about this, right? So think about this. So what is the value of doing action A in state S? What is the value of doing action A in state S? So it is the expected reward or expected return you are going to get for performing action A and following policy pi thereafter, right? You first perform action A and after that you follow policy pi. I'm not going to the future, right? I'm just looking at the pi is fixed. Just that one instance I am doing action A and after that I am going to follow policy pi, right? So you can think of Q pi SA is this, right? So we have already seen this, right? The first action is state is yes, first action is A, but after that I am going to follow policy pi. So we can write the equation like this, right? The value for this you can write it like this, and of course we can always write out the expectation. So there is no summation over A here. Why? Because A is fixed. There is no need to sum over A. So the summation is over only S prime and R. Summation is over only S prime and R. So you get probability of S prime R given S comma A times R plus gamma V pi S prime. Okay, so that's basically what it is, right? So now the claim that we are going to make is it is better to do A instead of pi of S. Better to do A instead of pi of S if Q pi SA is greater than V pi of S. Right? Remember, for a deterministic policy, what is V pi of S? Right? So V pi of S is basically Q pi of S comma pi of S. So that's what it is, right? So there is no, because the deterministic policy, there is no expectation over the action, over the different actions, because pi will be 0 for all actions that are not given by the policy, right. So, I can also say that V pi of S for a deterministic policy is Q pi S comma pi of S, right. So, it is better to switch to A, right, if Q pi SA is greater than V pi of S. If not, you are better off performing pi of S itself in that state. You do not want to switch to a different action. Okay. Then that makes sense, right? So, let us move on. So, now I just picked an arbitrary state S, right, and I said, okay, it is better for you to change from S to A, I mean pi of S to A if Q pi S comma A is better than V pi of S. But why should I stick to just one state? I could do this for all states, right. So, I can do this for all states and I will get a new policy which we will denote by say some pi prime, right, that is better than the old policy pi. In fact, what is the best improvement I can get, quote unquote, best improvement I can get is not just picking some action, right. What did we say? We will pick an action that is greater than V pi of S, right, but not just pick any action A which is greater than V pi of S, but pick the action A that has the highest possible Q pi, right. That gives you the maximum improvement over V pi of S. Does that make sense? Right. So, why pick some action that has a higher value than V pi of S? Pick the action that has the highest possible value for Q pi, and that will give you an improvement over the existing policy pi if one is possible, right. So, what we do is we pick a policy pi prime that is greedy with respect to V pi. Pi prime will suggest actions that are greedy with respect to V pi, right. So, what does that mean? I am going to select my next action pi prime of S as the action A that has the maximum Q value or as a maximum V pi resulting from taking that action A. So, what does this mean? So, I am going to take action A, right. I am going to look at what is the next state S prime and look at V pi of S prime and what is the reward I am going to get along the way, that is R. Putting all of this together essentially gives me Q pi SA, right. So, I am being greedy with respect to the current value function V pi. So, by greedy that's where the argmax comes in. So, if I am greedy with respect to V pi, remember, right, I am not talking about pi prime here. I do not know pi prime yet because I was given a policy pi and I have computed V pi, right, that we did in the policy evaluation stage. Right. So, now what I am doing is, okay, given this V pi for some arbitrary policy pi, I am trying to define a new policy pi prime that is greedy with respect to V pi, because this is potentially going to give me a better action to take in any state S. Okay. Now, if we do this, what do we guarantee? We guarantee that V pi prime will be greater than or equal to V pi. Remember, we talked about comparing value functions, right? So, V pi prime greater than or equal to V pi. What does this imply? This implies V pi prime of S greater than or equal to V pi of S for all S. Okay. So, some states it could be higher, some states it could be equal, I do not care, but in every state it is either greater or equal. Okay. So, V pi prime of S is greater than or equal to V pi of S for all S. So, this I will guarantee. Why I am not able to guarantee the greater than, right? Notice that I am only able to guarantee greater than or equal to, because right, I can guarantee greater than if I can say that the action I have picked will be greater than V pi of S, right. So, Q pi S comma A will be greater than V pi of S for all states, but I am not able to guarantee that because, what if it is already the best action is being taken under pi, in which case by moving to a new action, right, I will not be able to guarantee that I will be better, because this already the best action is being taken under pi. So, I can't improve on that. So, if I am already taking the best action, I can't improve by taking the argmax, because it will return the same action pi again. But if I am not taking the best action already according to this Q pi, then I will improve. That is why the greater than or equal to here. So, what we can guarantee is V pi prime is greater than or equal to V pi. Okay, I can't guarantee that it is always greater than. Okay, in the individual states it might be greater than, but some states it might be equal to. Great. So, now we have this policy improvement. But then what happens if I keep doing this policy improvement, then at some point I suddenly find that I do not have greater than or equal to, I have equal to. Right. So, what does being equal to mean? What does being equal to mean? It means that V pi prime of S equal to V pi of S for all S. Right, that is what it means. Correct? But how did I construct this V pi prime? Right, I constructed this pi prime by doing this argmax. Right, so I found this argmax, which is basically the action A that maximizes the summation, is giving me what pi prime is. So, the V pi prime is basically that maximum value, right. I have taken the action that gives me the maximum value and set that as the pi. So, if I want to compute what is the actual value function of V pi prime, it is that maximum value that I computed already. Right. Now, because they are equal, I will set it to equal. That is the reason I am able to set it to equal. So, now basically what has happened is V pi prime of S is equal to max over A S prime summation over S prime R P of S prime comma R given S comma A times R plus gamma V pi S prime. This should ring a bell. What is this equation? I have to go back many slides, but let me try that. That equation happens to be the Bellman optimality equation. That equation happens to be the Bellman optimality equation, right? So, this V pi prime is equal to V pi. So, this is basically equal to V pi, right. So, that means V pi of S equal to this. So, this is basically the Bellman optimality equation. So, we can write V pi prime, consequently V pi is equal to V star, because we know that the Bellman optimality equation has a unique solution and that unique solution is V star. So, we know that already, we have seen that earlier again on the videos, right. So, V pi prime is equal to V star is equal to V pi. You have seen that because that is where we started off, right. So, V pi is equal to V pi prime equal to V star, and both pi and pi prime, assuming they are different policies, right, are optimal policies. Right, and we can stop. So, we have now found a way to get an optimal policy. So, basically what we do, we start with some arbitrary policy pi, right, evaluate that policy, get V pi, now be greedy with respect to V pi. So, that is basically what we are here. So, we start with some policy pi naught, right, then you evaluate that. So, you get V pi naught, then you be greedy with respect to V pi naught, right. So, it is called the greedification step, right. It is referred to as the greedification step or the policy improvement step. So, you do the policy improvement step, and so you go from V pi naught to pi 1, right. So, you get a new policy. Then you evaluate pi 1, you get V pi 1 and you keep going, right. And then be greedy with respect to V pi 1, you get pi 2, go all the way until you end up with pi star, and then you evaluate that and you get V pi star. So, that is basically, right. This way of solving, it is called the policy iteration algorithm. Right. You start off with some arbitrary policy, you evaluate it, you get V pi naught, you improve it, you get pi 1, you evaluate it, you get V pi 1, you improve it, you get pi 2, you evaluate it, you get pi 3, V pi 2, you improve it, you get pi 3, you keep going until your V pi and V pi plus 1 whatever do not change, right. V pi k and V pi k plus 1 do not change, at which point you say you have come to an optimal policy pi star and you return the pi star and V star. Okay. So, this is one way of solving the MDP, and this is called policy iteration, and this is basically one of the workhorse, right. So, almost all the algorithms that you will see going down are some variation or the other of policy iteration, right. And so, it is very important that you understand policy iteration well, and so spend some time with this material. So, this is basically we know how to solve it, right. So, let us look at the algorithm version of it, right. So you start off with some arbitrary policy pi of s, right? And then as you did with the policy evaluation part, you start with delta equal to 0, then you loop around until your delta reaches a small threshold theta, and now you have the value function of pi, right? So at this point, you are going to assume that v of s contains v pi of s, right? Now you come. So you say that okay, the policy is not changed, it's not changed. You start off with a flag, right, setting that it's not changed. Now you look at what is the old action at pi of s, and then you find the new greedy action, right? This is, remember, this is my original v pi k, right, and this is my pi k plus 1, right? So if my old action, right, which was my pi k's action, is not equal to my new action, then I will say the policy stable is false. That means the policy has changed, so it is not converged, right? And now I do this for all states. Yes, even for one state the policy changes, then I won't stop. So if policy is stable, that means for all the states the action hasn't changed, then I will stop, right? And I'll return whatever was my last value function I computed, I'll return that as v star, and whatever is the last policy I computed, I return that as pi star. Okay. If that's not the case, then go back, right? Evaluate this new policy that I have obtained, because policy stable has become false. That means the action has changed at least in one state, right? I'll go back and re-evaluate this whole thing and keep looping around, right? So one thing you have to be careful about in policy iteration, right? So this is essentially, this is implements whatever I showed you earlier, right? Pi naught, v pi naught, pi 1, v pi 1. So it keeps doing that iteration until it converges. But there's one thing you have to be careful about. Suppose in a particular state, right, there are two actions, right, going up and going east. Let's say going up and east both have the same value, right? So when I do this argmax, right, I could, if there are two actions that have the same value, I could break the ties arbitrarily, right? Remember, I'm looking at deterministic policies. I can either go up or I can go east. So I can just toss a coin and say go up if it's heads and go east if it is tails, right? But the problem with that is that even if I have converged to one optimal policy, maybe both going up and going east are optimal, right? But what will happen is, because I'm tossing the coin, I'll keep flipping between north and east, so the policy might not have converged. It might look like the policy hasn't converged, even though I have found the optimal policy. I found one optimal policy, but it will look like the policy hasn't converged. So one way of getting around that is to make sure that in argmax, right, when you do this argmax here, so you break ties consistently, right? So what do I mean by that? So you have to make sure that if among the candidates that are there for argmax, right, so if there are like 3 actions that achieve the maximum, if one of them happens to be the old action, then you will take that, right? If there are 3 actions that are tied for a particular argmax, then you will take the action. If the old action is part of the 3, you will take that. That's a little cumbersome to check. So you can actually break ties consistently. How do you do that? You always take the action with the least index. If there are multiple actions tying for the maximum, you always take the action with the least index, or always take the action with the largest index. One of the two, either one will work, right? Take the least or the highest index. That will make sure that if there are ties, you don't keep oscillating between the two, so that you'll terminate on time. So this is something to keep in mind when you are implementing this, right? So finally, going back to what we did with I'm just giving you the example. This is not quite the policy iteration setup, but very quickly looking at it. So you start off with this. We start off with the random policy, right? And then you get the value function for it. But as you keep evaluating this value function, right? So this is the final value function. If I am greedy with respect to this value function, right? So what will happen? So here, what is the action I will choose? I can either choose to go north or I can choose to go east. I'll break ties and go north or east, right? So I'll just go north, right? Likewise here, what I do, I can either go here or go here, right? Here, what do I do? There's no go, just here, right? Likewise, if I'm here, I could either go north or I could go east. So like that. So I have multiple options. So here I could go here or here. This one only up, this one only up, this one only left, this one only left, this one only left, right? So, this is basically this is how my value function, my argmax is going to look like, right, and I will break ties consistently. I will get one policy, and it turns out that that's actually the optimal policy. In this case, policy iteration will converge in one step. So, I start off with a random policy, I evaluate it, find the value function, I be greedy with respect to that, and presto, I actually have an optimal policy. Right. So, hopefully, the example that you will see later, we'll look at more complex steps here. Okay. So, the next we will look at another algorithm for solving the MDP called value iteration. So, policy iteration, like I said earlier, is the workhorse, right? I mean, a lot of algorithms are different variations of policy iteration that we will see in the future. But value iteration also has a very important role to play. In fact, more often than not, that is the algorithm of choice for in the OR community for solving these problems. And it turns out that it's also very powerful way of looking at things for approximating the solutions as opposed to computing the exact solution. So, we'll look at it in the next lecture.